No, I'll just do it from here. All right. Slides are up. Hey, everyone. I'm Zviad from Dropbox. I'm an infrastructure engineer. And today, I'm going to talk about how we adopted Go at Dropbox, sort of why we did it, why not do what we were doing before then, and how we like it, and sort of what we learned from it, and so on. And sort of this is going to be the primary outline here. And let's see. Before I'll start to explain why we chose Go, I think we need to give a little background on sort of the Dropbox infrastructure and how it evolved. So originally, this is like, 2011, and it's a very simplified version of what the infrastructure looks like. We have two primary applications, basically. It's just two monolithic servers. We've got a metadata server that deals with the metadata. We've got a block storage server that deals with mostly just binary blobs. In reality, the actual architecture is a little more complex. Like there are separate clusters for serving, let's say, client traffic or web traffic and so on. But fundamentally, it's just like two binaries, and they're Python binaries. So even though the system is monolithic, it doesn't mean there's no abstractions. You can still have abstractions in a single binary. So for example, something like our distributed database library was built as a library. It was also in Python, and it's the only thing that sort of talks to databases. It's separated from the rest of the code. Works out fine. But at this point, sort of while we're growing and we're seeing building things as a library gives you ability to not worry about your deployment. It gives you ability to not worry about how you're going to discover another service and talk to it, or how to talk to it, because you can just call it out. However, from points of iteration and correctness, you really want to separate this out, make your library smaller, because you don't want to have to upgrade all your servers to deploy new code to your distributed database system. So we knew we want to get to sort of this point where we have a service, which is our distributed database service, which is doing most of the work and then talking to the actual database storage engines. And we've got the library that is much smaller. It's sort of more like an RPC client, and hopefully there isn't too much code there that changes. And this is the turning point into deciding how to build this service and what language to use in there. And I think first one is sort of tackling why not continue to use Python. So there are four main reasons that we were facing. So the performance is pretty well known issue with most of the interpreted languages. You just don't get that good of a performance and efficiency. But it wasn't even like the biggest problem in there. So correctness is a second one, where this is not just like correctness from like static type checking. It's similar to, let's say, if you were writing code in C, where you have one random library you imported, it had a bug, it sort of overrode random parts of the memory, and now your core libraries that were dealing with critical stuff are completely screwed too. And there is no real way to protect yourself from random libraries that you imported, let's say, some sort of logging library that you really didn't care. You didn't do your due diligence to make sure that code was well written. So similar stuff actually exists in Python too, because you might use C modules. Even the language allows you to, because you have so much flexibility, you can sort of like with one bad code really screw up data integrity and correctness of the rest of the stuff. Then third one is parallelism, which is I separate out specifically from performance, because it is different, where you might be able to make some enhancements to linear performance, but the lack of parallelism, we knew that it was going to be a pretty big stopper from building a service. And of course, the code refactoring is everyone who's worked in dynamic languages, that it's a ginormous pain. So even with like more tooling or static analyzers and so on, you're always kind of scared to rename a function. It's probably not a place you want to be. So the time came to like decide between this, three choices, and this is around 2.5 years ago. So we've got C++, we've got Java or JVM-based languages, but mostly just pure Java. And at that point, we had to go into consideration to So C++ sort of went out the first because we didn't have some sort of serious experience and expertise in C++. It's not like we've been doing C++ for a really long time. And we all knew that doing C++ well, even though there are definitely companies that have done it, requires a lot of work first to make sure your tooling is right, make sure you set up everything perfectly to reduce sort of what people can do with it. And we were pretty scared about the correctness part to, you know, one part not overriding everything else. The Java part was probably more subjective, where, you know, a lot of people have gotten their infrastructure to work at really large scales in Java, and it works. There isn't really anything too wrong with it. Except some people have had experience, including myself, dealing with JVM issues, looking at some of the code from like Apache, Hadoop, and HBase projects, and that was not something I wanted to do. So that was definitely subjective. I don't really have any true objective ways to say that why you shouldn't do Java. And on the Go side, we had some confirmation from people like YouTube's Vitess project. It's like a distributed database system that is all built in Go, and we knew they were running at large QPS, and we knew it sort of worked for them. So if we put enough effort into it, hopefully we get it to work. So some numbers, and I put this slide in here because I think it gives sort of a sense into when, like, once we wrote this initial project in there. So around 3 to 5 of us initially writing code, so we rewrote all our core libraries that we had internally, including, you know, our own RPC stack, our logging, monitoring, error reporting, a bunch of other stuff. And then around 3 to 4 months to rewrite the library into service. Since it was separated out, it was pretty easy to do. And we were done with the migration around, like, we fully migrated the system in 6 months. So this should tell you that it's pretty easy to be productive in Go. None of us had written a single line in it before that. It's pretty easy to be productive, and more importantly, this system was already doing, even like 2 years ago, we already had around 200, 300,000 QPS, and these are like not like small queues. They're actually, each one of them would be multiple database queries. And for that to work out of the box, all the sort of core parts of the system should have worked. So that should give you a sense of that it can work at scale pretty much out of the box. We didn't really have to do too many crazy things to get that to work. Otherwise, it would have taken a lot longer. Doing crazy things takes more time. So one big lesson that at least I've learned from it is if you are deciding sort of to do a, you know, maybe you're deciding to choose a new language at your company or something like that, do not take a toy project to start with it, because the initial code that you write is of extreme importance, all the core libraries that you write, and if it's for a side project that no one really cares about, maybe except for you, and that's how you're writing it, but your core parts of the libraries are going to end up not being high quality enough for that to be a success. So that's why, and also you're not really going to find out if your really important system is going to work in it or not. So it could be interesting to play around, but if you're sort of deciding to do it, it's more important and more useful to really take a really core system, try it out. If it doesn't work, at least you know it didn't work. Maybe you sank like 6 months in there, but at least you've found out that it's not going to work. So now some learnings into what sort of we took out from this experience of writing this. And after we wrote this initial service, Go quickly became a pretty dominant language to write all of our infrastructure services, primarily because our core libraries worked well too, like the ones that we wrote. So we started writing most of the infrastructure after that in Go. So some things that we learned in the writing part, so when we were writing libraries internally. So this is probably true for most of the new languages or even older ones that you have, is that having ability to easily refactor code is key to make sure you don't acquire huge code debt. And the way we achieve that is that all our code is in a single repo. And you know, it helps that Go has static typing, so you can rename stuff. And because builds take only a few seconds, it's pretty easy to actually check your whole project, no matter how large it is. You would have to get a much larger scale of code to really not be able to do mass refactors. So for example, I'll give some examples where like code refactoring really helped to make sure we didn't sort of stagnate. So when like writing a library interface, you always have this question of like, should I expose structs? Should I expose interfaces? I've got even an example here. Like let's say you've got a memcache client, could, write a struct client, it's got like methods on it and you have a new function. You will probably quickly realize this is going to work, but then you're going to need to test it or either swap out the implementation and so on. Then you realize you probably wanted to have an interface and then a struct. So if you can refactor the code, it's fine to make this sort of, initial setups, because then you're just going to change it. You're going to, grab your code and do some sort of replace on all of it. It will be fine. If you can't do that, or if let's say you have an open source library or something like that, this will generally sort of lock you into a potentially problematic setup that's not so easy to replace, because you're going to end up having something like client and client 2 or something like that. That's never fun. So another similar example to this is, and I guess on the structs versus interface parts, we realize that for the stuff that we we have open source libraries too, which are more libraries that are more mature, the ones that we know we're not going to change, where we pretty much everywhere we go with interfaces, because you know that even if today you don't need it, you're going to need it later on, and changing it, if it's in open source and it's out in the wild, you can no longer really change it in a backwards and compatible ways. So similar setup is actually with constructors when you're creating these objects. So originally you start with something like this. Let's take a hypothetical connection pool library. Originally you just create a simple one. You've got a single constructor. You take a list of addresses and it'll round robin between them, do stuff. It's fine. Then you realize, oh, you wanted configurable timeouts. Might make a new function that does new with timeout. Then you realize you wanted a load balancing strategy changes between round robin or more fixed strategies. At that point, you already realize that this is not looking too good. You're sort of adding more functions. If you can refactor code, this stuff is, again, a little bit easier to deal with it, because you can refactor stuff out from it. However, even in a sort of we haven't still found a really perfect way to do this that deals well with both having many optional arguments and especially having default values for those optional arguments in a way that's both safe, so it's not too easy to make mistakes. So for example, like a timeout is a really good example of this. If you take defaults to be your structs defaults, it will generally be 0. It would be really weird code-wise if 0 actually meant 2 seconds of a timeout, and you don't really want your default to be infinite timeouts. That's how your systems go down when things stop connecting to each other. So this sort of stuff, we actually haven't really found a really good sweet spot. Most of the times we go with this struct structure where we have a function that returns the struct with default values. Sometimes we've experimented using the pointers, where the pointer being nil defines that you haven't defined the value. But all of those actually have some slight issues here and there. So that's one part that is sort of requires some figuring out. Another important point that we discovered in writing the libraries in Go is that especially if you're coming from other languages, or if you're looking at a library written in another language, it's sometimes the first reaction is sort of to do it in the same way, and the most common one is when the libraries expose sort of callbacks to return the data. And copying this part into Go is going to make your library pretty limited and not compatible with the rest of it. And this one's probably the most important one, to really use the channels for your asynchronous value returning purposes, where you return a channel, because then whoever's using your library can combine that with all the other stuff that exists. So this is like one that you generally notice, like if people are sort of working on something and you've already done this before, most of the times probably in many other languages you would have used a callback. You sort of want to change the mindset. And there are a few other ones, but I didn't go into too many of them. One other part that we found that is pretty annoying to do is the collections and general data structures, something like sorting or sets and things like that. Fortunately, in most of the infrastructure type of services that we build, this doesn't come up too often. If it came up too often, we would probably be more annoyed. But it's like you just copy code sometimes. No, that's what happens. I mean, even standard libraries examples are leave something to be desired, including like sorting and so on. All right, so now after writing libraries, you probably also use third-party libraries. So one important part that we discovered from early on, and this was one of the reasons why we actually went with Go too while looking through the code, is that the standard library is extremely solid. Everything around like the TCP part, the HTTP part, that stuff works really well. And this is one of the reasons why the sort of building this type of infrastructure services works out of the box most of the times. As far as the third-party libraries go from open source, there's a lot of variance in there. We found some libraries that are pretty great. For example, we use the Zookeeper one from Canonical, like the Go ZK one that works quite well. We have a unit testing one also from Canonical project that also does its job. There have been some that didn't do its job and we had to rewrite it. That happens. So that's sort of you really want to be careful in there what you get into. And one part on the third-party libraries that we discovered is that you really don't want to do your network I/O in CGO. So for example, if you took let's say you wanted to build a Redis client and you're like, oh, I have this great Redis C library, I'm just going to wrap it with CGO, I'll be done quickly, you're going to lose a lot of the benefits that you get from having your Go routines, waiting, and that being efficient when you drop into the CGO to do your network I/O, especially if you have a system that's going to like fan out and talk to, let's say, 100 Redis machines. It's going to very quickly diminish the positives that you gain from the language and go to someplace worse. All right. So now, after writing code, we had to do some testing too, or maybe sometimes we did testing before writing code. Sometimes. So it was generally, this is sort of a probably controversial topic maybe in the Go community, but internally we've all agreed that if you want to write code, you should pick up a more real testing library than the one that's sort of built in, because it's the original one doesn't have enough features to let you really write tests in a more compact way, because you end up like writing a ton of stuff. Sort of what I mentioned about interfaces, those really come in handy. You generally don't need to do any sort of, if you come from dynamic languages, you've probably patched and mocked random functions in random modules. Those, you can't do them, and it's also a good thing that you can't do them. That's one of those parts that you probably shouldn't have been doing in the first place. But it happens if you have the ability. So if you want to do more advanced testing, so this is sort of once we evolved our ecosystem internally, we had some parts where we wanted to have more testing, especially around like fault injection. This type of stuff doesn't really exist. At least 2 years ago they didn't exist. I don't know if they exist now, but we had to build some of this stuff. So an example is like we had to build our own fault injection library that allows you to both inject errors inside the code execution and also inject errors in our RPC calls and so on, where it sort of asks the other server to pretend like it failed. So, all right, what's after testing? Now we've written code, tested it, we wanted to deploy it and run it in production. So deployment side, I'm not going to spend too much time here because everyone knows it's one of the best parts about Go, so already hear too much about that. So the fact that the binaries are statically built, you pretty much never really have much issues with. Once you have the code running, you can really easily like roll back to it. Even if you deploy a new version, when you roll back to previous one, you really don't have to worry about it. You don't need some crazy build system that allows you to build hermetic builds. Like, you avoid a lot of other stuff. I think it's also important to note that the fast build times also help you avoid a lot of like tooling and things. Like, you don't really need anything crazy about incremental building. Even with pretty large size projects, it can actually compile and build everything fast. So you can pretty much go a really long way with just go build and just check in all your code in a single Git repo and check all your third-party dependencies in Git repo too, and you're actually going to be fine. It's like not a crazy thing to do, which is not true for a lot of other languages if the compilation time can take forever. So, after deployment on the running in production, one of the most surprising parts that we faced was that well, maybe it shouldn't have been surprising, but the runtime turned out to be extremely solid, especially after Go 1.3. Pretty much never crashes. Well, not pretty much, it doesn't crash actually. It's mostly our code if it crashes. So that's pretty surprising for such a new language and we run like today we run probably at least few tens of, or if not even 100 millions of QPS probably in like individual services, like the database system that I was talking about. One part that is on the runtime part is the Go max prox variable. If you dealt with that, that one's definitely an adventure, sort of choosing what you want to do with that or how many processes you run on a single machine to really get, especially for low latency systems, this matters. What we've discovered generally is that running more processes will help with your GC because each one sort of, dealing with less stuff. And so we try to sort of max out our RAM if we can have, we just sort of still try to run a little more processes. Some of it, we've tried to play around with 1.5.2, but we've done enough tweaking that it didn't provide all that much help in there. So in debugging side, I think this is one other part where the tools out of the box work quite well. We didn't actually have to go into great lengths to add anything too crazy into it. The stuff that comes with like /debug on the pprof side, or your heap dumps or your go routines, stack dumps and so on, they're all perfectly fine for pretty much doing most of the debugging. Unfortunately, you can use GDB with Go, so if you're one of those people who likes GDB, I don't know if such people really exist, then you can't use it, so it doesn't work. Well, you can use it, but that's not called usable. The hardest ones to debug are the GC-related performance issues. So for those, we still haven't found really good ways to debug those fast. It takes like someone to really dive much deeper into like figuring out, because even with the profiling data and so on, you don't get a really good sense into what you need to be fixing or where the problem is, and it requires a lot more thinking. So we try to avoid that too much. So after doing all that, I'll just give some sort of situation of what's happening currently at Dropbox from Go side. We've got around 400,000 lines of non-generated, like actual humans wrote this code. Around 130 people write code into it, and the general trend is people become productive in it very fast. Almost pretty much all of what we would call an infrastructure is built in Go today, and all the new things that we build in Go. And we're starting to experiment a little bit for the product backends too. This stuff is still in Python, but there are sort of that's more of a different battle. And we're actually still using Go 1.3. We haven't migrated to 1.5. We're in the process of testing it out. But this should tell you one part about Go 1.3. It's because it's so stable and it works just fine. That's why we haven't migrated. It wasn't like there wasn't really any big problem in migration. It's just like it runs just fine. So generally don't change too many things when it works. So that's it. I'll take questions.